All right, welcome to the final session of NANOG 65. We'll have a few different presentations. First, Ari Fogel will present on network validation. Then we'll have Clinton Work from TELUS talking about IPv6 deployment experiences. And then we'll have the closing presentation by Betty Burke, the executive director. So, Ari, thanks.
Hi, I'm Ari Fogel. I'm going to be presenting to you proactive network configuration validation with Batfish. This is joint work with Stanley and Todd from UCLA, Louis and Ramesh from USC, and Meg, Ratul, and Jitu from Microsoft Research. So as many of you are probably aware, misconfigurations in enterprise networks are somewhat common, and in the case that they cause outages, they can be very, very expensive. But why do these misconfigurations happen typically? Well, one of the main problems is that when you're writing configurations, you have to specify a number of low-level directives for multiple different routing protocols. And then you also have to model the interactions between all these different routing protocols for mechanisms like route redistribution, administrative distance, BGP readvertisement, and with policy changes, and so on. So even if you get that configuration right for a single node, you also have to consider the sort of holistic way that all the different nodes communicate with each other. And it's really easy to get that wrong as well. So for example, we have this network in the center here, and on the top right you see there's this 10.0.0 network, and we have a simple intent that we want to implement for this. We want 10.0.0 to be reachable from the customer C on the left, from the customer here, and we want it to be unreachable from the rest of the network that's not involved in the path to 10.0.0. And I've implemented this using these configuration snippets that you see at the bottom here. So in order to make 10.0.0 reachable from C, you could see lines 3 and 4 on the left for the configuration of N2 here. What we do is basically, this is a directly connected network for N2, and for whatever reason, the operators decided to redistribute this connected network into OSPF with the metric that you see here. And that's to provide connectivity to 10.0.0. To make it unreachable from everywhere else on N3, the operator in lines 4 and 5 has installed a static route that just drops all traffic for 10.0.0 and redistributes that static route on line 5 so that its neighbors will basically send traffic there to be dropped. Now, if you're looking at this, you may notice that there's a problem here. I wonder if you can figure out what might go wrong. Well, if you actually were to run this, you would start to notice that some of the traffic that reaches N1 that's destined for the 10.0.0 network will go in the direction of N2 and then to N10 and then reach its destination. But some of it will go to N3 and be dropped. And this is because of equal cost multipath routing, which is initiated because these two routes have been redistributed with the same metric, and they both arrive at N1. This problem where you see that a packet can be delivered or not delivered non-deterministically based on some hash, we call it multipath inconsistency. So in order to find problems like this, we've developed a tool called Batfish, which is a proactive configuration safety checker. It's available online. You can take a look after this talk if you wish. And we've used it to find real bugs in real networks. And our favorite quote from one of the operators of the networks that we analyzed is that with respect to the prefix that was dual assigned from yesterday, one of my NOC guys stopped by today to ask what voodoo I was using to find such things. So that was pretty fun. So the way Batfish works is that you input your router configuration files and maybe some information about external BGP advertisements that you want to model, as well as your topology. And you also provide some assertions that you want to check and then outcome violations. Batfish is divided into these 4 stages that you see here. First, we just process the configurations, then you analyze them with assertions based just on configurations. And then we are actually able to use all this information to generate the forwarding tables that would occur if you were actually to run this network. And then furthermore, you can write assertions about the forwarding tables that you'd like to check. So stage 1 is pretty basic. We parse the configurations. So a line like this first one you see here on N3 would be converted to this fact about OSPF interface costs in our model. So you see the node is N3, the interface is N3.1, which you see from here, and the cost is 1, which you get here. And we get similar information about the topology and convert that to facts that we're able to handle. In stage 2, we basically try to figure out all the different simple problems that might arise during initial check of the configurations. For instance, if there are any syntax errors, that'll be reported. Or common problems like having an undefined reference, let's say to a route map that doesn't exist, would be reported here. And on top of that, we also have a language that we've designed for asking queries about the configurations. And we've also provided a library of common checks that you may want to use. So for instance, you might want to find out if IP addresses are reused across the routers in your network. So you would input that assertion, and an example output you might get is that this particular IP address that you see here is assigned to these two interfaces on these two routers, and you may want to deal with that. Another common thing that operators wanted to see was whether loopback networks were exported into OSPF. You would need this, for instance, if you wanted to run MPLS or IBGP on top of your IGP network. And so some simple output right here would just show you that, well, actually loopback 0, on this particular router is not running active or passive OSPF, so the network's not going to make it into the OSPF rib. And of course, you can design your own queries as well, and I'll talk about that later. So after you process the configurations and now you have a model to handle all of them, we also are now able to generate the forwarding tables. So we start with some basic facts from the configurations, like the fact that, let's say, a particular network may be exported into OSPF. And using all of these facts together, we're able to compute the actual ribs that should result if the routers are working properly according to the spec. So for instance, that network being exported from N2 may make it onto N1 with such and such cost. And from there, we're also able to figure out what interface everything will go out. So we have the forwarding tables as the final output of that step. Then in stage 4, we can actually ask questions now about the forwarding table. So if you recall earlier, there was a multipath consistency violation in the example network. And if you were to ask about multipath consistency, whether it holds, then you'll either get the answer, yes, it does, or you'll get a violation that's specified in terms of a packet that would actually violate multipath consistency. So in this case, if you were to create a packet and insert it at N1 over here and give it these parameters, then it would be a violation because according to the routes I showed you before, some of it would go to N10 and be accepted, and some of it would go to N3 and would be dropped. Furthermore, when we find these example packets, we are also able to give you a virtual trace route to show you what is actually happening. So for that example packet in the previous slide, you see that on one path that it could take, it'll go from N1 to N2, then from N2 to N10 and be accepted. And on another path it could take, because of ECMP, it could start at N1 and go to N3, where it's promptly dropped because of the static route that is discarding packets for that network. So Batfish has been quite an undertaking. It's written in several programming languages, namely Java for most of the logic, Antler for the parsing, and Datalog for the forwarding table generation. We also support many different routing languages. We support Cisco iOS, NXOS, Juniper, Arista, Quanta, and other similar router configuration languages. We support a wide variety of features, including route redistribution, internal, external, OSPF, BGP, communities, route maps, policy statements, etc. And again, this is a real tool. If you want to check it out to see whether it'll support your network, you can go to batfish.org and shoot me a line, and I can help you out with that. So we actually tested out Batfish on 2 large university networks as well as Microsoft's network. Unfortunately, I won't be able to tell you anything about the results at Microsoft, but I can explain what happened at these university networks. So they're qualitatively different, these two. The first one has a decentralized design at the core. Well, this is managed by the Network Operations Center team, and then they have a different team for each department, which is configured as a different autonomous system, and the core peers with all of these departments using BGP. In the other university network we analyzed, it's much more centralized. It's all one autonomous system, and the different departments are partitioned by VLANs. In addition to, on these 2 networks, we tested a variety of forwarding plane properties, 2 of which I'll discuss. The first one was multipath consistency, which I've shown you earlier. And the second one is a check about fault tolerance. So we want to see whether reachability will be impacted by the failure of any single link in the network. So if you look at this network below, on the left there's a customer that is advertising two routes, 2.2.2.0 and 3.3.0. And on the right, this network has route maps that will accept the 2.2.2.0 network at N2 and will accept advertisements for both networks at N1. So if you were to actually turn off this link, then you would see that 3.3.0 is no longer reachable because there's nobody to accept advertisements for it anymore. So this would be a violation of this fault tolerance property that we want to check. So as I said, we tested these properties on these two networks. In this column, you can see the total number of violations that were detected initially by our tool. In this column, we show the violations that were confirmed to be real problems by the operators. For multipath, they were all confirmed to be problems, and for fault tolerance, we had some false positives simply because the way the network was organized, some of the departments actually had different names, but were really the same department. So it appeared that there was no fault tolerance, but there really was. For net 2, again, all the multipath violations were confirmed to be real. And because we had incomplete topology information about the way the VLANs were set up, there were some false positives in detection of fault tolerance because we would have maybe multiple interfaces underlying a VLAN, so really no loss of a single interface would have been able to cause a loss of connectivity. Of these violations, the majority of them were fixed. In the case for net 1, the multipath violations were not fixed immediately because a discussion needed to be had about the peering situation between the core and a particular department where this violation occurred, and haven't yet heard news back about what they ended up doing. In the fault tolerance case for both networks, none of them were fixed because to actually fix it required laying down new lines, and that was not something that they were ready to do just at that moment. But all the multipath violations for net 2 were in fact fixed. So I'm going to do a quick demo for you with a network that I designed that is a sort of analog of network 1. I've written Cisco configuration files for this example network and planted some bugs in there. So let's take a look. So basically what we've done is we've zipped up the configuration files that I've written for this network and uploaded them. And now what we're going to do is process them. You can't see here, but down here, it's parsing and converting that to our unified format that we use to represent configurations. That's done. And now we're going to generate the forwarding tables for that network. Now, in addition to be able to checking forwarding properties on a single network, we can also look at forwarding properties related to the difference between two potential versions of a network. So once this is done, we're also going to generate another data plane, which is, another set of forwarding tables, which is going to be representative of the same network, but with one configuration file modified. And then after that, we're going to try to see what the difference is in reachability between those two versions of the network. So the first one is done. Now let's do the second one. And while that's running, let me just show you some of the configuration files so you get an idea of what this all looks like. Oh, I'm sorry. One moment. Right, so here's the network that we're actually analyzing. There is a tier of border routers, which is connected to a tier of core routers that serve as route reflectors, which are connected to the distribution layer. And this distribution layer appears with individual academic departments. So in this example, there's just one department and one host behind it. And also there's two upstream ISPs that are separate autonomous systems that this network peers with. So let's go back and see if this is done. It appears that it is. So let's take a look at what has actually happened so far. So right now we're checking for parse errors. And if you look on the right, you see that there are none. So let's move on to another simple check. Oh boy. Excuse me one moment. Sorry, this UI is very fragile. If you type something in the box, it becomes very hard to show anything there. Excuse me one second. should be able to pick up where I left off. Anyway, that's all been processed, and now we can move on to analyzing the forwarding planes. So let's pick a question to ask. So for this network, you may want to know whether IPs are reused on different interfaces. So we can ask this question and see the result. So if you take a look here, what it's saying is that on AS2 border 2, which is one of the border routers I showed you, interface loopback 0, there is an IP assignment of 2112, and that same IP is also assigned to AS2 host 1 loopback 0, which is the host at the very top of the picture I showed you earlier over here. We may also want to check to see whether OSPF contains all of the loopback networks. So let's check for that. So it detected 2 violations here. The internal autonomous system at the top, AS2 dept 1 and AS2 host 1, are not actually exporting loopback 0 into OSPF, so those violations were detected. And we can also check actual, forwarding properties. So the first one we're going to check is, oh, I'm sorry, one moment. Just 1 second. Yeah, okay, I entered the wrong text. I just need to start that over. So what this is basically doing is trying to discover all the packets that might violate multipath consistency, and then afterwards it figures out what would happen to those packets for some samples that it gives us. It's usually quicker. There we go. So the output is shown on the right here. Oh boy. I'll just pick one particular packet that it found. So it says that if you insert at AS2 department 1, which is the second one from the top in the picture here, a packet with a destination IP of 3022, which would be destined for that ISP on the right in the bottom of the picture. And if the destination port on that packet is telnet, then these are the 4 different paths that packet could take. And the first path, you see it starts at AS2 department 1, goes through this set of routers and interfaces, eventually reaches its destination at AS3 core 1 and is accepted. However, if it takes a slightly different path, which exists because of ECMP, then it will go and be dropped at AS2 core 1 because of the inbound ACL, whose name is block telnet, line 0, which is the first line of that ACL. So now we can actually take a look at AS2 core 1, and in fact, there is an ACL there called block telnet, and this line just simply blocks telnet, so that's confirmed. So now, for the other property, let me just get it started, and I'll discuss it. So while that's running, there on this AS2 dept 1 router here, there is an ACL, which I will show you in a second. On Fast Ethernet 1.0, which is the one pointing up towards the host, there is an ACL called restrict host traffic in, which is supposed to only allow traffic from, above in the incoming direction. But the operator sees this and thinks, well, how come we're not also restricting traffic in the other direction? And in fact, there is an ACL defined to do just that in this file here, restrict host traffic out. So to fix this, the operator makes an assignment of that ACL in the outgoing direction on that interface. And let's see what happens. So what we see on the right here now is that in the original scenario with the configs that are unmodified, there's a packet that could be sent from AS1 border 1, which is from the ISP on the left, with the destination IP shown here. That destination IP is for the host at the very top. And in the original scenario, that packet will be accepted no matter which of the equal cost paths that it takes. Now, in the second scenario, where we've modified one of the configuration files, we see that in each situation, it gets to AS2 Department 1, and then is dropped because of an ACL called restrict host traffic in line 1 of that ACL. So the problem here is that the operator actually had a typo when they assigned this ACL, which is perfectly feasible in practice. Instead of assigning the outgoing ACL, they assign the incoming one. And so now what happens is all traffic to any host in that department ends up getting dropped. So that concludes the demo. And the presentation. So we have a survey that we would like you all to take if you operate networks, because we want to add feature support that people actually use. So please go online and take it. It should only take about 10-15 minutes. And if you have any questions, feel free to email me at arifogel@ucla.edu. Thank you.
We have time for questions in the room, and we have questions in the room.
Good morning, Matt Pitak, Yahoo. So I saw like cool IPv4 addresses. Does this grok IPv6?
I'm sorry, because of the echo.
Does this
The question
understand?
is, does it support v6?
We have parsing support, but because none of the networks that we analyzed used it in any real capacity, it's not supported yet, but I'm sure. In fact, we've talked to several operators here already that have asked that very same question, so that'll be the top priority for feature addition.
Thank you.
So, just a quick follow-up. So neither Microsoft nor UCLA are using IPv6?
What's that?
I think the question was,
I mean, I'm pretty sure they are, aren't they?
I think the question was,
Sorry, Michael Sinatra, ESNet just
UCLA
floated that
does
bomb.
not support v6, question mark, or
How do you know I analyzed UCLA? Well, I did, but I
that-
can't tell you anything about that.
That network that you displayed looked an awful lot like UCLA's network.
I don't know what you're talking about.
Any resemblance to characters and networks living or dead, purely coincidental.
Hi, do you have any plans to support XR and ISIS?
Yeah, actually, we just added parsing support for XR a couple months back. So there is some basic stuff. Generally, whenever we look at a new network, we have to update the parser just because of the way different constructs are used and people use different features. But yeah, the basic support is there, I believe.
For ISIS as well?
You said for XR?
But he also said
XR and
ISI.
Right, ISIS as opposed to exclusively OSPF.
Oh, ISIS. Yeah, there is support for ISIS.
Cool, thanks.
Sorry, it's a little boomy up here with when things come in from the audience, so
Yeah,
patience is appreciated.
it's not synchronized, so I just hear everything like.
Any other questions? Okay then, thanks very much, Ari.